So consider the free body diagram of a small fluid volume, and it has the shape of a wedge, and so we're going to have pressure forces acting, of course, on every single of these walls, and we're also going to have the weight of this. Let me draw the weight right here, the weight of this fluid, and we're going to have pressure forces acting on every wall. So let's imagine that we have our axis here, so that this is Z and this is X and this is Y. This is a small fluid volume, and so it's going to have dimensions. On this side is going to be delta Y. So this distance here up to here is delta Y. This distance up to here is going to be delta X, and this distance up to here is going to be delta Z. And so the volume here is, we're taking only this wedge shape, so it's 1/2 of delta X, delta Y, delta Z. And the pressure forces, well, we have all of these different walls that we can look at. On this wall, on this top wall right here, on this top surface of the wedge, we're going to have a pressure force which is equal to, let's call it PS, because it acts on an inclined plane. We don't know yet the value of that. PS times the area here is delta X, this distance here, times let's call it delta S for the time being. Delta S is going to be all of this distance over here. Okay, we'll calculate it in a moment. We do have this angle over here, delta. So the pressure on this bottom wall, the pressure force on this bottom wall here, is going to be P, well, P in the direction Z, times the area, which is delta X, delta Y. That's the bottom area here, delta X times delta Y. The pressure acting on this wall is going to be Py, P in the direction Y, multiplied by this area here, and this back wall over here is delta X times delta Z. We have that wall, we have the bottom, and we need the two sides. We're going to ignore the two sides. We can see that those cancel out. But we're just going to look at all the forces here. So let's see, this one is going to have an angle. So let's draw here the angle. This is going to be equal to the angle theta that I've drawn here. Let's see, we have this weight is going to be the volume times the density and the gravity, so we know the weight. And we're going to now simplify this a little bit by considering a unit thickness on the X direction. Therefore, we're saying delta X is going to be equal to 1. To simplify, remember the only forces are weight and pressure, because this is a piece of fluid, a volume of fluid that is at rest. And so the forces in the X direction, in this case, do not balance the weight. Only the forces in the Y direction balance the weight. And so we're going to do force balance in the Y direction. So Py delta x, delta z. Delta x is equal to 1, so we forget about that, and the component in that direction is going to be ps ds, which we can always calculate, times sine of theta, so that's that component over here of that force. And now we can apply the fact that ds sine theta is the same as dz, and so we get a very simple result, which is that py is equal to ps. Okay, that's our first result. These two pressures are going to be equal. I have taken it as equal to 1 to simplify the whole thing. I've just taken it to be unit thickness. And now we're going to do force in the z direction. In the z direction. And now we're going to include the weight, of course. We have p z delta y, and that one is pointing up. Every other one is pointing down. The weight and this pressure are pointing down. So we have the pressure component here is ps delta s times the cosine of theta, and now we have also the weight, which is gamma of the liquid times delta y delta z divided by 2. Again, delta x is taken to be 1. So now we can use the fact that delta y is equal to delta s times cosine of theta to get pz minus ps is equal to gamma delta z divided by 2. All the dy, the delta y's cancel out from here. Okay, but what we're going to do, the following thing that we're going to do is that at a point, we want to look at the pressure at a point. So now we have some expressions. We know that py is equal to ps, but we're going to look at a point and make delta z. We take the limit when delta z tends to 0, and when we do that, we get that pz is equal to ps. Pz equal to ps, which indicates the final result of this derivation is that the actual value of the pressure is independent of direction. It is the same regardless of the direction. So the pressure that we have actually here called ps, py, pz, all of these pressures are the same. The pressure at a point in a fluid at rest is independent of direction. Therefore, it is a scalar. It is a scalar field. It only depends on the point. It doesn't depend on direction.